Hello, Assalamualaikum. So today we are going to present our mini project, which is the journal by Robert L. Constable. The title is The Role of Finite Automata in the Development of Modern Computing Theory. Alright, so here is my team. I am Norhasliana Amiza, binti Abdullah.
My name is Iman Izzaty, binti Zamri.
My name is Nurfa Hadirah, binti Tabri.
So here is the content of our presentation. First, introduction. Second, historical origins, basic definition and construction. Third, early automata theory and its influence. Fourth, modern themes and conclusion. So we move to the introduction.
Okay, first of all, we will go through introduction. In this presentation, we will discuss based on an article titled The Role of Finite Automata in the Development of Modern Computing Theory by Robert Constable. In the article, he examined a few important discoveries about finite automata and the influence of those discoveries on the modern theory of computing. He mainly concentrated on those aspects of automata derived from Klein's fundamental theorem and those aspects directly related to logic. I am going to present about historical origins, basic definitions, and construction. First, we will talk about the historical origins. In 1943, the concept of finite automaton arose in the paper written by Warren McCulloch and Walter Pitts. McCulloch and Pitts described neural nets in terms of the formulas of the predicate calculus with a time parameter. In 1948, John von Neumann summarized that any functioning that can be defined logically, strictly, and unambiguously in a finite number of words can also be realized by a formal neural network. In 1951, Professor Klein, influenced by McCulloch and Pitts' works, produced his very influential paper, which titled Representation of Events in Nerve Nets and Finite Automata. Next is basic definitions of finite automata. The first definition is, let sigma be a finite set of letters. A word on sigma is a finite sequence of letters. The empty word is denoted as lambda and has no letters. Let a set of all possible strings be the set of all words including lambda. The second definition, a finite automaton FA is an algebraic structure where sigma equals to S, delta, S naught, F, where S is a finite set of states, delta is the transition function, S naught is the initial state, and F is the set of final states. A finite automaton also can be represented by a transition diagram or state diagram. The next is regular expressions. To describe the events accepted by a finite automaton, Klein introduced the class of regular expressions. Regular expressions are like algebraic terms over constants. Here is an inductive definition. The first definition is an empty set or lambda are regular expressions. The second one is, if A is an element of sigma, then A is a regular expression. The third one is, if E and F are regular expressions, then so are E plus F, E times F, and all possible sets of E. The fourth one is, other than the first, second, and third definition, nothing else is a regular expression. The last one is Klein's theorem. Klein introduced regular expressions to describe the behavior of finite automata. He defined an event is a regular over sigma if and only if there is a regular expression which denotes it. Below are the theorems from Klein's paper in 1951. The first theorem is Theorem 3. To each regular when over sigma, we can find a finite automaton over sigma which accepts it. The second one is Theorem 5. The set accepted by a finite automaton is a regular event, whose defining regular expression can be constructed. Klein used the term representable event for our term accepted and used the word event instead of language. The theorem numbers are from his paper.
Hello, back to me. So I am going to discuss about early automata theory and its influence. The first one is minimization and equivalence. It is important to examine the possibility of constructing a smaller comparable device. When using finite automata to simulate hardware and software development, it is essential to evaluate if a smaller similar device can be constructed. When this state minimization algorithm become more important, in reality, it is more efficient version was motivated. So here is the theorem from Hertkopf state that there is an O n log n algorithm to minimize a finite automaton. Next, it is lead to feasible auto-equivalent to test method. This reduction technique also leads to feasible auto-equivalent testing approach. The minimal auto is unique. Therefore, one way to reduce the automata to its minimum form and to check whether they are the same. The minimum form is an automatic canonical expression. Alright, so here is the theorem from Hertkopf and Karp. Say that there is an O and a power of negative 1n algorithm to test the equivalence of two finite automata, where n is the maximum of the numbers of states and a is the Ackermann function. So next is algebraic view. The definition due to Lerard, an equivalence relation R over sum of range is right invariant if and only if whenever x ry then x z ry z for all z belong to summation of range. An equivalence relation is of finite index if and only if there are only finitely many equivalence classes under R. So we can use this to show certain events are not regular. So the last one is non-determinism. So non-deterministic automata are free to make choices at a certain step of their computation. If any of these choices leads to an accepting state, the input is accepted. For example, given alpha accepting A and beta accepting B, we can construct a non-deterministic machine accepting AB. To accept AB, simply connect alpha and beta by considering the accept state of alpha as if they were start state of beta and adding the appropriate transition. It is appear that these non-deterministic machines are more powerful than deterministic machines.
Now I will talk about the next subtopic, which is modern things. Okay, first of all, what is finite automata? Okay, finite automata are the central not only to the subject of the automata theory and formal language, but they are such a fundamental descriptive tool that appear in every branch of computing theory. Two of the most important areas of the modern computing theory are, first, the theory of computational complexity, that dealing with the efficiency of algorithm, and the next one is the theory of programming logics, that dealing with the reliability of the programs. First, I will talk about the computational complexity. In the mid-1960s, computer scientists actively began studying a theory of asymptotic computational complexity. One of the first areas of investigation related to the computational complexity to Professor Klintz and P.X. work on a subrecursive degree. The primitive recursive functions were given very interesting interpretation in terms of computational complexity hierarchies. In the early days of complexity theory, one of the major concerns was to find the natural examples of problems which require a very large computing resource. In example, requiring exponential time. It was therefore remarkable when the Albert Year discovered that Ubin's decision procedure for SNS was non-elementary, and even more remarkable when the Mayers and the Stokely discovered that the equivalence problem for the extended irregular expression, those involving union, decimal, asterisk, and also dash, though known to be decidable. was non-elementary. Moreover, they discovered good evidence that even the equivalence problem for the union and decimal and also asterisk will be very hard. And furthermore, the equivalent problem for union and asterisk alone will be hard in the sense that finding a polynomial time algorithm will be a major breakthrough in the theory of computing. Extremely useful in terms of usefulness, it is extremely useful. It tends to guide the research in the algorithms and give you the intuition on how to proceed with the certain problems. Computational complexity theory is basically the taxonomy of the computational problem. Okay, next I will talk about the logic of programming and automata. Here we are seeing in the late 1970s a fascinating confluence of stream in Professor Klein's work. In the mid-1950s, he had finished his RAND report and was thinking further about realizability and the application of recursive function theory to logic. Now, 30 years later, the technique of automata theory are being applied to logic of programming in somewhat the same way. In example, to provide the computational semantics. When the computational task can be described independently of the program solving it, then the program can be regarded as a constructive proof of the assertion that the task is accomplished. This method of achieving reliability was proposed by Alan Turing and by the Goals team for numerical programs. In the numerical case, the statement of the computational task is often a familiar mathematical assertion, and the program formalizes a familiar informal algorithm. So, the method is a little more than adding specific algorithm content to ordinary theorems. This idea has been interestingly refined by John Kraft, Robert Lloyd, and more recently, Carl Hall. These computer scientists have extended the methods of non-numerical problems and have proposed specific ways of incorporating modern algorithm notation into the proof. The need to guarantee that practical programs perform as required has led to a class of logic dealing directly with the modern high-level programming language. This focus on program has also led people to consider the reliability problem as one of the program verification or program proving. But in fact, from the logician's point of view, it is a special class of proof that is being verified, namely proof that use program. The term program proving seems more acceptable because its ambiguity allows one to interpret it as giving a proof that involves writing a program.
Finally is the conclusion. The terms finite state machine and regular expression are basic to the vocabulary of computer science. In conclusion, this paper examined a few important discoveries about finite automata and the influence of those discoveries on the modern theory of computing. It also concentrates mainly on those aspects of automata derived from Klein's fundamental theorem and those aspects directly related to logic. That's all from us. Thank you.